Welcome to this video on discrete set points. If you want to position a system accurately, for instance in a robot application, you don't want to introduce infinitely high accelerations. After all, these create very high disturbance torques and forces, and that does not help in achieving high positional accuracy. In a second order set point profile, where the velocity is trapezoidal, the accelerations are bounded. Now, how do you implement such a second order set point in a discrete environment, for instance in a digital control with a fixed sample frequency? That is what this video is about. So discrete systems can only update information on fixed sample times. In between we don't have any information. So set points, trajectories, must be designed exactly on this discrete time grid, otherwise we make an error. And in this video you learn how to design a correct discrete trapezoidal motion profile. Suppose you want to move an object according to the following specification. We have a trapezoidal speed profile, so a second order motion profile, and we want to have a movement as fast as possible. And we have other requirements. We have distance requirement, which says that the total distance should be exactly 0.1 meter. And we have a maximum speed requirement, so the maximum speed is bounded to 0.1 meter per second in this example. And we say, well, my speed profile is symmetric, so my acceleration and deceleration are the same. And in this example, they are 0.6 meter per second squared. So in that case, we can draw a so-called speed time plot in which we have the time on the horizontal axis and the speed on the vertical axis. And here we see the trapezoidal speed profile. During T1, as T0 and T1, we accelerate, and you see the speed going up linearly. In between T1 and T2, my speed is constant, so my acceleration is 0. And between T2 and T3, we see the deceleration in which the speed goes back to 0 again. So my maximum speed is 0.1 meter per second. My acceleration over here is 0.6 meter per second squared. And the total distance is the area underneath this speed time plot, which is equal to 0.1 meter. Now let's look to some timing aspects. We can say when we start off at 0 seconds that t1, my acceleration time, is v over a, which is 0.1667 seconds. The distance during acceleration, so in between t1 and t0, is 0.5 times a times t1 squared, and that is equal to 8.3 millimeters. And because we have a symmetric velocity profile, the distance during deceleration is equal to the distance during acceleration. So it's also 0.0083 meters or 8.3 millimeters. Which leaves us with this speed time profile in which we can see that during acceleration and deceleration we have a distance of 8.3 millimeters, which we have already established. So we can say that during acceleration and deceleration, the total distance is equal to 2 times that value, which is equal to 0.0167 meters. So during constant speed, so in the area between T2 and T1, we have to move on a constant speed, and that position which we have to move is equal to the maximum position, what was our requirement, 0.1 meters, minus that 0.0167 meters, which is 0.0833 meter. So that leaves us with the following timing requirements. T1 is the acceleration time, which was 0.1667 seconds. T2 is equal to T1 plus the position at constant speed divided by that speed. So we end up with 1.0 seconds, T2 over here, and T3 is T2 plus the acceleration time, and we end up at 1.1667 seconds. So that is my timing profile. But suppose we want to realize this profile in a digital environment with a frequency which is equal to 1 kilohertz. Then the horizontal time grid is defined by the sample time, which is equal to 1 over the frequency, which is 1 milliseconds. So we can only have sample times of integer values times that sample time of 1 milliseconds. So times t1, which was 0.1667 seconds, and t3, this value, are not on this sample grid. So they need to be recalculated, otherwise our profile cannot be made. So this is our strategy. In words, first of all, we are going to round t1 and t2 to the next value on the discrete grid, so on the discrete sample time grid. So these are integer multiplications of my sample time. Then we adjust the acceleration based on the distance specification. And of course, the acceleration resolution setting must be high enough. But suppose we have a data bus of 32 bits, then the resolution for the acceleration is 1 over 2 to the power 32, which is really, really, really accurate, especially compared to the sample time of 1 millisecond. And then we have to calculate again if we don't exceed the maximum speed because we have a new acceleration and a new t1, of course. So that is our strategy. So in equations, our strategy looks like this. First of all, we round t1 and t2, and we do that by multiplying t1 times the sample frequency. We round that value and divide it again by the sample frequency. And now we have a t1, which is on the sample grid. And we do the same thing with t2. Then the acceleration should be equal to the deceleration, so t3 is equal to t1 plus t2. And we calculate the new acceleration. So how do we do that? How do we calculate the new acceleration? Well, we can do that using the following equation. The total distance underneath this curve is equal to the distance underneath this triangle, then the distance underneath this rectangle, and again the distance underneath this triangle. So it's 0.5 times 8 times t1 minus t0 squared, this triangle, plus this rectangle, which is t2 minus t1 times v, plus the area underneath this triangle, which is this expression. Well, that looks like a big expression, but fortunately we can simplify this equation. So that should be our step 1. And because the acceleration time and deceleration time are the same, and we start off at t0 is 0 seconds, we can say s equals 0.5 times a times t1 squared. This area underneath the acceleration part, that triangle, but that is equal to the deceleration part, this area underneath this triangle, which is this part of the equation, plus t2 minus t1 times v. So we end up with this equation. S is equal to a times t1 squared plus t2 minus t1 times v. We can also say that v is equal to a times t1. So we can eliminate v from the previous equation. And then we get s is a times t1 squared plus t2 minus t1 times v. And v was equal to a times t1. So it's equal to a times t1 squared plus t2 times a times t1 minus t1 times a times t1. So this is the same expression as that expression. So s is equal to t2 times a times t1. We can also see that directly from this graph because the acceleration time and deceleration time are the same. So this triangle is equal to that triangle over here. And then we have a rectangle, which is equal to t2 on the horizontal axis and v on the vertical axis. And the area underneath this rectangle is equal to t2 times v, and v equals a times t1. So the total distance over here is equal to t2 times v, so t2 times a times t1, which is this expression. And now we can calculate the a from that expression, and that brings us with a is equal to s over t1 times t2. So now we have to do one last thing. We have to check V if the velocity does not exceed the maximum required velocity. So a times t1 should be smaller or equal to the maximum velocity. So in MATLAB code, when you want to implement it in MATLAB, you can say, well, t1 is equal to the rounding of t1 times fs, and then divided again by the sample time. And in this expression, I use ceil from ceiling, which is rounding to the nearest integer value. We do the same thing for T2. We say T3 is to 2 T2 plus T1. We calculate A from the expression A is S over T1 times T2, and we check V, and V should be smaller than the maximum value, and V is equal to A times T1. So that's all the MATLAB code which is needed for a second order motion profile on a discrete sample grid. So conclusion. What you have to do is you have to check always if the sample times are located on the sample time, so on the sample time grid. And if not, you have to recalculate the trajectory times. You have to make sure that the resolution to modify the acceleration is high enough. For instance, when you have a 32-bit data bus, it's not a problem. But when you have a very cheap microcontroller, for instance 8-bit, you definitely have to do the calculation again. And of course, for other set points profiles, similar strategies can be used, but of course they're much more complex. For instance, a third order motion profile, when you have to do the calculations, it's much more it's much more difficult compared to the second order motion profile. When you want to know more about set points and set point design, please see my video Set Points and Motion Control. Well, that's all. Thank you for watching.